Okay, we have finished the topic of spot speed studies earlier. We have started the topic of travel time. Okay, and in the last lecture, we did one example for travel time calculations as well. And I mentioned that these calculations are basically coming from the same topic of spot speed. So there are no new equations here. Okay, this is the example which we did, and this is a new example. Okay, and the data is given as a in the form of a bar diagram. So this is something new in this example. Instead of having a table or numbers, you have the data in the form of bar diagram. So on the x-axis of the bar, you see the travel time values. On the y-axis, you see the frequency of those values. So for example, the first value is 150. How many times 150 was observed? You can see on over here 1. How many times 160? 1. How many times 170? 0. Okay, how many times 200? 5 times. Okay, so you have the frequency and you have the travel time values. Okay, these values are done for a 3-mile segment. Okay, and these are 20 values. Okay, it's written over here 20 runs. So one run means one observation of travel time. Okay, so run is the term used for observation of travel times. Okay, so it's a 3-mile section. They're asking for average speed and 95% confidence interval of travel speed. Okay, so the same thing which we did in the previous example. In the last example, they give us numbers directly. Here we have data. Okay, to calculate the average speed, I must calculate average time. I will use distance upon time. So for average speed, I need average time. So these are the equations which we have used for the case of spot speed. Okay, the one at the bottom is for the average time. So I need capital N, small n, and capital S. What is capital N? Total number of values. How many values we have? 20 values. Okay, for example, if this line was not written here, okay, let's say they did not tell me they did 20 runs, I can count it from the frequencies. So capital N is the summation of small n. So you get the small n for every bar, which is the number on the y-axis. Okay, so 1 plus 1 plus 1 plus 2 plus 5 plus 3 plus 1 1 1 3 again, then 1. So if you add the y-axis values for all these parts, you will get the capital N. Okay, and similarly the small n are these values themselves. Okay, the value for each bar is small n, and the value on the x-axis becomes s in this case. Okay, it was s the speed, but since we are using the same equation for travel time, s becomes the travel time over here. Okay, so n into 1 for this bar, small n is 1 and s is 150. For this one it is 1 160, then 0 and 170, 0 and 180, then this one is 2 and 190, and so on and so forth. Okay, so you will do the summation of the y into x for all these bars. Okay, and then you divide by 20, which is the total of n. So can you tell me the mean over here? How much is the mean? Yes, calculate the mean of this thing. Yes, what is the mean travel time here? By the way, your calculators have this function. They can directly do this for you. Summation n into s upon n. And even this one as well. They can do this one as well. Okay, so for whatever divided by 20. How much? Okay, so this is my mean time now. Okay, so mean speed will be, I have 3 mile section. It is written with a graph. It's a 3 mile section. So this, and the time must be converted to hours. Okay, so this will give you average speed in miles per hour. Okay, how much is that? How much the mean speed? $49.4, yes. Okay, so this is your mean speed. Now confidence interval, they are asking for confidence interval. Okay, so 95% confidence interval, as we have seen in the last lecture as well, is mean plus minus 1.96 E, where E is S upon square root of N. Okay, now I have the mean, I have N as well. So in the E equation I need S and N. Now S is standard deviation. Okay, for standard deviation we have to use this equation, the top one. Okay, so N minus 1 means 19. X bar is your mean value, 218.5, mean of travel time. Okay, mean of travel time. I will calculate 95% confidence interval of travel time first. Okay, so I will do 218.5 plus minus 1.96. Okay, and E is S, which I don't know yet, square root of 20. Okay, so the important point is that you are taking confidence interval of travel time, and then from that travel time you will calculate the speed. So you will not take confidence interval of speed directly. You cannot do this, okay, because the data is for travel time. So you always have to go through travel time. If the data was for speed directly, then you can do it. Okay, so very good. Okay, so just for the sake of others, I will go back to the equation. Okay, so summation n on the y-axis and s is on the x-axis, so n into s square. You will do now what you are doing here, n into s only. Now you do the summation of n into s square, capital N 20, x bar 218.5, n minus 1 is 19, and you do this. Okay, so what was the standard deviation, Bayan? How much was the standard deviation? Just for the sake of others, so we can write the equation completely. What is the standard deviation? 14.03. Okay, now just a word of caution or a check. Whenever you calculate mean and standard deviation, you can apply a check. Okay, the check is that mean should be more than standard deviation. Okay, mean should be more than standard deviation. If mean is not more than standard deviation, that means either you have a problem in your calculation or a problem in your data. Okay, so you need to correct something in the end. Okay, so what Bayan is telling me here, the range is for this thing. Okay, the 95% confidence interval. So 218.5 plus minus 1.96. Okay, S value is 14.03 divided by square root of 20, and this gives you this range. Okay, now to calculate 95% confidence interval of speed, I'll use this range with the distance, do distance upon time. Okay, so 3 upon 205.4 Okay, so this will give you the upper value, and then you do 3 upon 232.5. So this will give you the lower value. Okay, okay, fine, good. So did I write it somewhere? I didn't, right? Okay, so you can just, okay, so thank you. Can you give me the speed values here? Mean is 49.4, which you told me earlier, miles per hour use. 38.29. Are you sure? Because mean was calculated using 218.5 in seconds, and then you are only going like 30-40 seconds up and down, so the difference should not be too much. Should be very close to the mean actually. The mean is 49.5. Then the other values, the 95% confidence interval should be very close to 49.5. Yes, anybody else? What is the 95% confidence interval of speed? What are these values? Two 81 point, what is this? This is mean speed. Yes, mean speed. Then yeah, you have to add the mean speed, sorry. So yes, I missed it. No, it's fine. Yeah, it's fine. Okay, so these are the values then. Okay, anybody have any questions? Okay, so moving on. Okay, now we have done two examples. In one example we used running time, in another example we used travel time. Okay, the difference between running time and travel time is the delay. If you add the delay, it becomes travel time. If you subtract the delay, it becomes running time. Okay, so running time is without the delay. Another way to find out the delay is using the method of probabilities, using the method of chances. So you look at what can cause delay on the highway. What are the things on the highway which can cause delay? And if that thing causes the delay, what is the average value of the delay because of this thing? Okay, and then what is the chance that this thing can cause a delay? Okay, so for example, if you see this example, the thing which can cause a delay is the signal. So on the highway there are two signals. Okay, if you are stopped, so obviously it's a chance, right? You may be stopped, you may not be stopped. If you are stopped at any one of these signals, you are delayed by 40 seconds. So if you are stopped at both signals, then you are delayed by 80 seconds. So average delay for each signal is 40, both 80. Okay, then they calculate what are the chances that a vehicle does not stop at any signal. Probability. What is the probability of that? So 0.569 meaning 56.9% probability that the car will go through both the signals without stopping. Must be very good signal, something from heaven, right? And then what is the probability that a car will only stop at one of the two signals? So which one doesn't matter, both of them have the same delay, right? So if the car stops at any one of the signals, the chance for that is 30%, 0.30, 30%. And the remaining chance is that the car will stop at both the signals from start to end. Okay, so this is like the delay which you don't want, right? So for each case, we know the chance and we know the resulting average delay. So what is the total delay expected in this case? Okay, so if you are giving the chance and the average value and we have to add them together, then we do the weighted average. Okay, so delay will be for example, the first value of delay, first possible value is 0, right? 0. So 0 multiplied by the chance of 0. Anything multiplied by 0, I'm just filling the equation. Okay, so this whole thing will become 0. But the next item is, the next possible delay is 40 seconds. What is the chance for 40 seconds? 30%. So 40.3. Then the next one is 80 seconds. What is the chance for that? 13%. The remaining, okay, 56.9 here, 30 here, the remaining is 13.1. Okay, so this is 80. So this will give you the expected total delay of the highway. How much is that? How much is this value? Okay, 22.48 or 5 seconds approximately. Now just what I said earlier, if you have travel time and running time, then delay is travel time minus running time. Okay, so this is one way of doing it. If you have both the values, running time and travel time, and the other way is you use the probability and the average value of delay for each probability. Okay, again something which we have done earlier for the case of spot speed studies, calculating the number of samples. Here they call it the number of runs, not the number of samples but the number of runs. Okay, so this is the equation which we are going to use. This equation is used with 95% confidence interval. Okay, I already showed you the derivation for that. And in this equation we need E and S. Okay, so they have given me two sets of values, plus minus 2, plus minus 5, plus minus 10, one set of value. The other one is 5, 10 and 15. Okay, so this 5, 10 and 15 is standard deviation, S. And this 2, 5 and 10 is the E value, plus minus. Okay, E is given as plus minus. Okay, so even if they don't write it, you should know. Okay, so E is the expected or the allowed error. Okay, or tolerance, you can say. So these values are given. So we have to find out for each case how much will be the number of samples. Okay, I can go to how do I see my okay. So we have to calculate the number of samples using this equation. My E is changing and my S is changing. The E is going from 2 to 5 to 10 and S is going from 5, 10 and 15. 5, 10, 15. Okay, so for each combination we have to calculate the n value, the number of runs. Okay, it's very simple. Can you give me the first value? I can tell you this value is 3.84 and this value is also 3.84. Okay. Okay, so you can see, okay, give me the next value. I just want to fill one row and column. $96, okay. So which value is 9? This is 96. Okay, give me this one or either this one, anyone. This one or this one, so we can fill at least one row and column. 216. Okay, if you give me this one, then I can move on. How much is this one, the last one? S is 5 and E is 10. How much? $16. Okay, so you can fill the rest of the table. It's very easy. Okay, but what I want to highlight, when standard deviation increases, you need more samples. Okay, and the logic behind that is the variation in the data is increasing. The standard deviation is a representation of variation in the data. We call it a measure of dispersion. So when you have more dispersion in the data, you ought to collect more samples. Okay, and E increases means your tolerance is increasing. You are allowing more error. So if you are allowing more error, then you need less samples. Okay, so there's a problem here. This should not be 16. This one cannot be 16. 196. Okay. Okay, so the point being, so now you see that, if you know the rules, if you know the pattern, then you can check your own mistakes. Okay, so how do I know there's a mistake? Because it does not follow the pattern. What is the pattern? That when E increases, you are allowing more error, you need less samples, and vice versa. Okay, same, and the opposite happens with standard deviation. Standard deviation increases, data dispersion increasing, that means you need more samples. So whatever value I get will be more than these two values. Okay, and so on and so forth. Moving on. Okay, so this was a very easy example. Now we have this one. So thank God I have opened Excel. So it's these values are collected from 5 runs. Okay, and so each value is like an average of 5. Okay, and you see the cumulative length from point 1 and the cumulative travel time from point 1 as well. Okay, and the delay is given for each section meaning between 2 points. Okay, so the first value is 10 between point 1 and 2. The next value is 30 between point 2 and 3. Okay, so 30 is between these 2 points, and last value is 14. So 14 is between these 2 points, and so on and so forth. And again, number of stops between each 2 points are given. Okay, we are not using them in this example, but just to show you, and we have also seen it in the previous example as well, number of stops, the one which I showed you in the last lecture. Okay, so the first part is you have to find out the travel time and the travel speed and the running speed for each section. Okay, travel speed and the running speed for each section. So let me take it from here. Okay, take the picture from here and go to Excel. Okay, so I'm going to delete what I don't need. It's a very large picture. Okay, so section, first of all I will mix sections. Okay, each section is between 2 points. Okay, so 1 to 2, my god. Okay, then I have 2 to 3, then 3 to 4, then 4 to 5, 5 to 6, 6 to 7. Okay, now for each section I need the travel time and the running time. Okay, so travel time is given cumulative. Okay, so what I need to do is I will subtract it to find out the travel time between each 2 points. Between 1 and 2 is the same value. Okay, 2 minutes 5 seconds, doesn't change. Okay, there's nothing before this. Okay, so as it is. Now this one I subtract 450 minus 205. Okay, so 450 minus 205, and the answer will be 245. Okay, next one I'll subtract 730 from 450. Okay, so 730 minus 450 is coming from here. Okay, 730 minus 450. Okay, and the answer will be 4 minus 7 is 3, and 50 minus 30 is not 50 minus 30, 330 minus 50 seconds means 240. Okay, so in the same way you will keep on subtracting them. The next one is 910 minus 730. So 9 minus 7 is 2. Okay, and 210 minus 30 will be 140. Okay, then 1027 minus 910, okay, it will be 117, and then 1154 minus 1027 is 127. Okay. Okay, so all values are good. Any questions? Anybody has any questions? Obviously you are doing it. Okay, moving on. Yes, I'm here. Okay, now for running time. Okay, so running time means travel time minus delay. Okay, so this is my travel time and delay is given here. These are my delay values. Okay, so I will subtract them from the travel time. So first one is 2 minutes 5 seconds and 10 seconds of delay. Which is 155. Okay, then 245 minus 30, that's 215. Okay, then 240 minus delay 25 seconds, so 215. Okay, then 140 minus 42, 058. Then 117 minus 47 is 030, and 127 minus 14 is 113. Okay, so everything is same, right? No problems. So moving on to the calculation of running speed and travel speed. So now you need the distance as well. The distance also cumulative. So you have to find out the L value for each section as well. So the first section has a length of 1. Okay, 1 mile. Cumulative is same as is for this section. For the next section, I will do 2.25 minus 1. Okay, because they are cumulative. So 2.25 minus 1 gives 1.25. Okay, the next one I'll do 3.5 minus 2.25. So which gives me again 1.25. It was 3.5 minus 2.25. 1.25. Okay. Then the next one, 4 minus 3.5, 0.5. Next one is 4.25 minus 4, 0.25. The last one is 5 minus 5, 4.25, which is 0.75. Okay, now if you want to calculate travel speed, it will be distance upon time. Your distance is 1, in this case 1 divided by time. Now time is in minutes and seconds. Okay, so you have to convert it into hours. So it will be 2 by 60. It's 2 minutes 5 seconds, right? So 2 by 60 plus 5 seconds will be this one. Okay. So 1 is the section length. We have 2 minutes of time and then 5 seconds of time. 2 minutes and 5 seconds. So this is for converting it to an hour. Okay, and the same thing will be done for the other sections as well. So can you give me the travel speed values here? This is how much? The first one is how much? 28.8. Okay. 27.3. 28.1, 13, 18, what? How much? 11.7, okay, and 31. Okay, for the running speed, you'll do the same thing. You'll take the same distance, but divide by this time. Okay, running times. Okay, so the first one will be 1 divided by 2 upon 60, sorry, not 2, 1 upon 60 plus 55 upon 36. Okay, 31.3, then 33.3, 33.3, because these two values are same. Okay, this one 1.25 and the both are 1.25 distance and 2 minutes 15 seconds time. Okay, next one. 31, 30, 46.9. 36. Okay, 36.9. Okay, again a check. Okay, that running speed is always more than the travel speed, because travel speed is slowed because of the delay. Okay, so when you took out the delay, then the running speed would be higher, obviously. If there is no delay, then both of them will be equal. If there is no delay, then both of them will be equal. Okay, but in this case we had delay in all the sections, so running speed is higher. Okay, so it should always be higher. you're not getting it more, then you have a problem. Okay, this is the graph plotted for the delay. Delay was given and the travel time we calculated, and for drawing the graph, the entire travel time is converted to seconds. So if it was 2 minutes 45 seconds, they converted 2 minutes to seconds plus 45, and so on and so forth. So you can see here the section with the highest travel time is section 2 to 3. Okay, but the section with the highest delay is 5 to 6. Okay, the section with the highest delay is section 5 to 6. So which one do you think is more problematic? The one which has the highest travel time or the one which has the highest delay? Which one is more problematic for us and for the drivers? The one which has the highest travel time or the highest delay? Yes, the one which has the highest delay, because the highest travel time could be because of the length, okay, or could be because of the design speed of the highway. So if you go back, you will see that, or if you go to the Excel sheet I have, okay, so you see the section, okay, these sections have the highest length as well, so obviously they are supposed to take more time, okay, but this section has a very small length, 5 to 6. It has a very small length, but because of the delay it is taking so much time. So you can actually cover it in 30 seconds without delay. Okay, so the one which has the highest delay is the more problematic one. Okay, so this is the plot of travel speed and running speed, the same values which you have calculated, and you can see the running speed is higher. The red line is always higher because the blue line has a delay. Okay, now let's say on the same segment somebody wants to collect a new sample, so they want to calculate the number of samples required. They are taking the allowable error to be plus minus 3 miles per hour and 95% confidence interval. Okay, so we have to calculate the number of samples required using these values. Okay, now we have already seen the equation for number of samples required, which this is the equation. Okay, in this equation I already have the value of E. It is given in the question. Okay, 3 miles per hour. I need S. Okay, now S is the standard deviation. S means standard deviation. Now since I already have these values and I have them in Excel, I can calculate the standard deviation directly. Okay, now keep in mind the equation which I am using here is not for frequency distribution. The equation which I am going to use for standard deviation here, or the one which Excel uses, is for a number of values when the values are given separately. So you have now 6-7 values, okay, without frequency distribution. The previous examples which we did for spot speed and travel time, values were with frequency distribution. Okay, so you cannot do the same with those values because you have to use the big equation there which we have used. In this case I can use Excel. So how to use Excel? Okay, you do STDEV, standard deviation, okay, bracket, and you can select all the values. Okay, the first value has formula, so I will just add it here myself. Okay, so this is a standard deviation for the travel speed, and for running speed I'll do the same thing. This one and the first value, because it has a text in it, that. Okay, so this is for the running speed. So you can see when the when I took the standard deviation with delay, it was much higher. So delay causes variation in the data. Higher standard deviation means more variation in the data. So when you have delay, you have more variation in the data. And then we have running speed, which has less standard deviation. Okay, so now I have all the values I need. So if I calculate number of samples from here, it was 3.84 S square. So this value square divided by the E square. So E is given as 3 and this. Okay, so number of samples required according to this speed is 24. And if I go with this one, so 3.84 and as a square divided by 3 square. Okay, so if I go with this speed, I only need 2.6 samples, and if I go with this one, I need 24 point something samples. Okay, so in both cases we will round up. Okay, in both cases we should round up. So when you do the rounding up, then this one becomes 25 and this one becomes almost 3. Okay, now if I go back to the question, they have mentioned something else as well. They have mentioned they want to calculate how many test vehicles are required. Okay, so test vehicles are, I told you, there's a method for collecting travel time data, which is known as a test car method. So you hire a car. So they are saying we want to hire cars to do this sample for us, and each car will take 5 samples. Each car is available for 5 samples. Okay, either because of the gas or because of the time, whatever. Okay, so each car is available for 5 samples. Okay, so how many cars should I hire? So if I go with this one, I need 25 samples and each car is doing 5. So I need 5 cars then. Okay. Okay, 25 I need total and each one is doing 5, so I need 5 cars in this case. In this case, obviously I only need 3 samples. If I hire one car, that's enough for me. That one car can go up to 5 samples, so 1 is enough here. Okay, so now the question is, if you are doing this, then how many samples you would go for? Will you go for the 25 or will you go with 3? Just tell me. One speed is giving 25 samples, the other one is giving 3 samples. So in the end, you will go with which one? 3 or 25? Yeah, okay, we should go for the higher one because that's better for us. Okay, moving on. Okay, in the earlier slides I mentioned this thing which is called a travel time contour map. Okay, so actual file contains, what will you do with it? I'll see, because I just opened in a file, is like some attendance sheet or something. I'll see. Okay, and I deleted the previous example to do this one. Anyways, so what is the travel time contour map? As you have mentioned, you have studied travel time, or sorry, you have studied contour map in surveying. So a travel contour line shows some common feature, right? In the case of surveying, the common feature is elevation. In the case of travel time, the common feature is travel time. So in surveying, you always have a benchmark. So you are measuring elevation using the benchmark. In the same case, the same concept is applied here. When you are measuring travel time, you have a benchmark as well. So if you look at this travel time contour map, my benchmark is here in the center. Okay. So in a travel time contour map, you have a central point which acts as a benchmark. Then from this benchmark, you measure travel time in different directions and you set up your ranges. So in this map, you can see they have set up the range of travel time to be 15 minutes and 30 minutes. Okay, so you set up your ranges. These are the ranges we have, 15 minutes and 30 minutes. So you see 2 lines here because I have 2 ranges, so you see 2 contour lines here. This is the closer one is for 15 minutes, the larger one is 30 minutes. Okay, so 15 minutes from where? From my benchmark. 30 minutes from where? From the benchmark. So this point is 15 minutes from the benchmark, and this one is 30 minutes from the benchmark, and so on and so forth in all directions. So now you can see that doing a travel time study on one highway is not enough to produce this map. You have to do it in the entire region. So you have to go from the benchmark in all directions of the region so that you can make this travel time contour map. Okay, why do we make this map? This map shows us if you are going to build a new facility for the public, then the travel time contour map tells you from which areas people are more expected to come towards this facility, because people take decisions on the basis of travel time, especially if the facility is like a hospital or a bank or a mall. Then travel time plays a huge part in the attraction of that facility. Okay, so if you are selecting which mall should I go for, you will invariably select the one which is closest to you. Okay, provided that you have good offers there, right? And good merchandise there. But anyways, you will always prefer the nearest one which has your required items. So this travel time map tells me, okay, if the people are coming within a 15-minute range, travel time range, then I can expect it from these areas. And if my facility is like an airport, so airports are very rare. You may drive for an airport even for 1 hour as well. Okay, now in today's situation, people are driving to Dammam, which is like more than 2 hours from here. Okay, so including the time on causeway and everything. So people are, so then that airport can say that yes, people will come to me even from these areas as well, and they can design their capacity, their parking and their facilities according to these people. Okay, so a travel time contour map tells you from which areas people will be attracted towards your facility, because that attraction is on the basis of travel time and also depends upon the type of facility you have. The more rare is the facility, the bigger is the attraction area. I give the example of airport, very rare, so the attraction area is bigger. If you take the example of a smaller facility like a mall, then it's very common, so the attraction area will be smaller. This is another diagram which we can plot for a travel time survey, a travel time study. It is called as the time space diagram or time distance diagram. Let me enlarge it. Okay, so on the x-axis you have the distance, on the y-axis you have the time. The car started moving from here, and the solid line is telling you how the car is moving. Solid line. Okay, so you can see there are parts where the solid line goes vertical. Okay, so going vertical means what? Time is changing, distance is constant. Okay, so the car is actually stopped here. Okay, so obviously for creating this diagram I need to know exactly for every point how much was the time. Okay, so I need an observer, or I need some device which is giving me time at each and every distance. So once you plot this diagram, you can calculate the average speed as well. Average speed is total distance upon total time. So you take the total distance from 0 to the end, and you take the time from 0 to the end on the y-axis. So you will get the average speed, and for this diagram, speed is the slope, distance upon time. Okay, so you plot this diagram according to the slope, which is equal to speed. Okay, so the time distance diagram can give you the location of the car at every time of your stopwatch. It can tell you the duration of the stopping. Okay, so I know I can see from here to here the car was stopped. How much is the time? I can look at it from the y-axis, and so on and so forth. Okay, now we move towards another study which is connected to travel time. We have discussed it earlier as well, which is the delay. But now we are talking about delay studies for intersections. So delay for intersection is different. You cannot just take it from the travel time. Okay. So we will discuss now how to get the delay for the intersections. Now we have discussed stop delay before. Okay. So now delay at the intersection is stop delay plus something else. Okay, we call it the control delay. So the delay which is measured at the intersection is called as the control delay. Why? Because at the intersection you have a control device. That device controls how people should move, like a signal or a roundabout. These are control devices. So that's why we call the delay as control delay. Now what this delay includes? This delay includes stopping. It includes deceleration before the stopping, and it includes acceleration back to the normal speed. Normal speed here is termed here as ambient speed. So ambient means the normal of the highway, the normal speed of the highway, ambient speed. So when you are coming close to the intersection, you are going at a high speed normally. As you come closer, you reduce your speed because now you see that I'm at an intersection, I may have to stop. So this reduction is because of the intersection as well. So that's why we count it in the delay. Okay, the delay starts when you have started to reduce your speed. Then you reduce your speed, then you stop, and then let's say you have started moving again. Now you have found the opportunity to move again. So the signal became green, or there is no car coming from the direction, so now you are moving again. But now you have started moving from zero. Your speed was zero, and now you have started moving. Okay, so now you need some time to get back to your normal speed. That time is also part of the delay, because that time also happened because of the intersection. If there was no intersection, you would have continued at your normal speed. Okay, so that's why deceleration plus stopping plus acceleration back to normal or ambient speed is all part of intersection delay or control delay. Okay, we'll use some other terminologies with it later on. Okay, now we will discuss the delay for two types of control devices: signals and roundabouts. Okay, but I don't want to start the procedure for it now because I want to finish it in one lecture. So hopefully after the Eid we will be doing it. Just a reminder, I told you earlier as well, until the situation goes back to normal, just wait for my instruction for your project work. I know it may be difficult for you in the end to do it in the last few days, but it's better to stay inside and not be killed because of me, you know in this situation. Okay, so until everything goes back to normal, so I'll reassess after Eid if you are coming back to physical or not. Otherwise I may change the project. Okay, so just wait for my further instructions for the term project. Okay, so I will not start this procedure now. I'll go back to this one. And okay, people who didn't do the code, please